about the dynamical systems. I don't know, you heard about the dynamics. What about his behavior? Oh, he's very dynamic, very dynamic, right? Dynamic, correct. You are correct. Dynamical system is very dynamic. So in the second lecture, I'm going to talk about what is dynamical system and why we study dynamical system. I hope you understand about the content, what is dynamical system. Two things. What is the dynamical system? Why we are doing dynamical system. Two things. So here is my email address here. Oh, I'm sorry. This is website. My email address is what? khle.cnu.ac.kr. So you can, if you have any questions, email me please. Okay, let me start. The first review. The first lecture we discussed about why we do dynamics, the mathematics, and what are characteristics of the modern maths, and why mathematics is important. And the two words that characterize the modern mathematics are derived and abstract. Must be, these concepts should be based on the logic and the intuition. What is abstraction? Abstraction is the process of extracting a basic structure from a mathematical concept on Rn. And the dynamical system is a field of modern mathematics. Nowadays, okay, what is dynamical system? In Wikipedia, yeah, you like the Wikipedia. In Google, Wikipedia, then a dynamical system is a system in which a function describes the time dependence of a point and wow, difficult, forget it. Difficult, forget it, no. I like the next sentence, look at here. If you visit the Oxford Math Institute, in the institute there is a dynamical system group. In their website, what is dynamical? Common sense definition of a dynamical system is any phenomena of nature evolving in time. So look at me. This is dynamics. Any natural phenomena. This is phenomena evolving in time. Now here, as time moving to here, this is dynamics. You can meet Oxford Math Institute in dynamical system group. In the Oxford Math Institute, there are many research groups. There are many research groups. I don't know how many. One of them is dynamical system group. If you visit there, this is dynamical system. Wow. Very general. Yeah, got it? Any phenomena evolving in time, that is dynamical system. A lot of, look at here, a lot of natural, real-world problem can be expressed by various types of equation. Sometimes ordinary differential equation, partial differential equation, stochastic differential equation, stochastic partial differential, etc. Of course, functional equation, many equations. Right? Depending on the situation. Sometimes this phenomena can be expressed by OD. Sometimes this phenomena expressed by PD. Among the PD, many things. Navier-Stokes equations, reaction differential equations, many different type of equations. Stochastic equation, this is ODE with the noisy term. This is PDE with noisy term. So real-world problem can be expressed a lot of different type of equation. So what is solution? Or solution of a differential equation is a function f, one variable function or multivariable function or other type of function which is satisfied given equation. Oh, that is, you know, the middle school, high school, you learned about the equation. Differential equation is to find the primitive function, one variable, multiple this one. But it is not easy to find the solution of given function equation. Very difficult. Natural phenomena, okay, real world problem can be expressed by the differential equation. Various type of stochastic differential equation or partial differential equation can be expressed by equation. But not easy to find the exact equation. No, almost very few. So, even though such you find the solution, it is more difficult to understand long time behavior of the solution. It is periodic, it is recurrent. What is the limit set? Not easy. Finally, I mentioned about Poincare. What he said. Oh, math. What is mathematics? Mathematics is the art. Okay, who are you? Very good artist. We are artists. We are artists. He introduced a new method to find a long time behavior without finding solution. Without finding solution of ODE. For this, he introduced the notion of solution of ODE, abstract notion. Abstract notion is important. What is abstraction? Already I explained. Two words that characterize modern mathematics: generalized and abstraction. Abstraction of solution. Who? Poincare. How? How he did? This picture and the previous picture are different. This is a mathematician, previous one is an artist. Same person. I'm going to tell you through the model. For example, consider ordinary differential equation on Rf. This is vector notation. This is a scalar notation. Scalar, vector. What is vector? What is scalar? Point in R is scalar. Point in R2 is vector. Point in R3 is a vector. Point in Rn is a vector. Right? Point in R is a scalar. Just to simplify. Here we are going to introduce abstract notion of solution. So abstract notion of a solution, this is the key. Modern mathematics, generalization and abstraction is important. We are going to abstract the notion of solution. Okay. Suppose f is sufficiently smooth so that the existence in ODE, I'm sorry, just forget it. What? If f is sufficiently smooth, then if you take a point, there is a solution. What is solution? Function. Solution is function. There is a function, unique function. We assume. And the continuous dependence, it means if you start the initial point is very near, the solution is near. That is continuous dependent. Then what? Then the collection of all solutions of a given ODE can be expressed in one function. Who did? Poincare did. Who did? Poincare did. Okay, define a function in such a way. For any point in x0 in here, for any time in here, x of t, what is x of t? Unique solution of ODE with the initial condition x0 in here. Here, P is called the dynamical system on Rn induced by ODE. This is a definition of dynamical system induced by. So, one ODE induces one dynamical system. ODE is an equation. Dynamical system is a function. Note that important P has the following important properties. What is our goal? What is two that characterize modern mathematics. To characterize modern mathematics, what? Two words.
Generalization and abstraction.
Abstraction. What is your name?
Kanmani.
Huh?
Kanmani.
Kanmui. Mui is over there, Professor Mui is over there. Kanmui. Kanmui. Thank you very much. Oh, after lecture, can I contact you? We can discuss some mathematics. Very good. So important thing is we have solution of the equation. We are going to abstract the notion of a solution. We are going to abstract the notion of a solution. We are going to abstract. Right? This is the motivation. This is good. But to abstract, first we have the phi. What is phi? That is the dynamical induced by. What is this one? This is the collection of all solutions. If you take a point, then time. This is a solution. So phi can, this point is changed, then there is another solution. So phi can be think as the collection of all solutions. Then phi has the following three important properties. What are we going to do? We are going to extract. We are going to extract some properties. We see that it is a mass with three conditions. He has the three conditions. He is the collection of the solutions, right? He has the three conditions. Now, we are going to abstract. We are going to extract three conditions from the model on Rn. We are going to extract. We are going to give, so we are going to, because we have the continuity. Continuous means at least the space must be topological space. In the case of topological space, we can say the continuity. So this is the dynamical topological space. We can abstract. This is it. This is it. So we can define such a way. A dynamic, what is that? A dynamical system or flow on a topological space is a map, this one. Instead of Rn, here is X. Instead of Rn X, with the three properties, same. Right? Why you define such a way? No, model from Euclidean space. Euclidean space. It's abstract. Similarly, you can define the notion differential dynamical. No, forget it. Do not. There are many different types of dynamicals. Take a photo for me. Good. Okay, good. Here, most important concept is orbit. What is orbit? Abstract notion of solution. In the theory of equation, in the theory of differential equation, in the theory of partial differential equation, in the theory of stochastic differential equation, what is the most important? Solution. The abstract notion of solution is orbit. Orbit. See, vary. Natural phenomena evolve in time. There is a time, so it's a dynamic process. In fact, it is an abstract notion of solution. Abstraction. Here is the orbit. If you have a second arrive here, t second arrive in S plus t second is arrive here. Because of the one, uniqueness of the solution. Because of uniqueness of the solution. Next question is this one. Poincaré did from the ODE to make the dynamical system, right? Then, can we think of the dynamic induced by PD? The answer is yes, definitely. This theory was developed by Jack Hales, George and Henry in all these 80s. Can do, same, not different. I want to tell you finally, there are many different types of dynamical systems. Philosophy are same, not different. We want to understand the solution. What is solution? That is abstract notion of solution is orbit. So notion of orbit is important. Notion of solution is important. Let me give you a partial differential equation, but don't need to. It's difficult to find the solution. So more difficult to do this one. Partial differential. And existence uniqueness, then this is the fundamental problems in PD. Well-posedness. Some people are doing work hard in well-posedness in PD. When existence, all of the life, they just concerned about when solution is exist. Which equation has solution? Sometimes when the solution is unique. Continue. And how much regular? How much regular? Solution, how much regular? This is most difficult. How much regular? C1 plus 1/2, C1 plus 1/3, C1 plus 1/4. Very difficult, delicate. But don't worry. In our case, PD is well posed. There is a unique solution. Then the collection of the solutions of PD can be expressed by one function. Can be same idea, not different. This way, this is solar space, L space, the defined function, unique solution. Here, as is called infinite dimension, is a dynamical system. To distinguish, why infinite dimension? Because L2 omega is an infinite dimensional Banach space. Banach space. Dimension is infinite. So usually, the dynamical system induced by the PD is called the infinite dimensional dynamical systems. Then, S has three important properties also. Same, not different. Not different. First, continuous, same. Three actions, same. Infinite dimensional Banach space. So we have to abstract again. Abstract. What is the two words that characterize the modern mathematics? Two words. What?
Generalization and abstraction.
Very good. Very good. Abstraction. So I'm going to abstract. This is the infinite dimensional diagram from Banach space. Nothing. Okay, then what is a lot of concepts and theories in dynamics like shadowing, hypothesis shadowing, extension. This is don't need to worry about it. Can be derived in the infinite dimensional and so same. Philosophy is same, not different. What about? Can you think about the dynamic induced by Stokes differential equation? What is Stokes differential equation? Differential equation with the white noisy term, more complicated. Also, can you think about the dynamic induced by the Stokes partial differential equation? Partial differential equation with noise. The answer is yes, we can do it. We can do it. So what is Stokes differential equation? Ordinary differential equation noise term, small error around the orbit. We can extract and abstract. Then we have the random dynamical systems. It's called the lambda because of the error term, the noise term. Random. Also, Stokes partial differential equation, noise term. So we can abstract. That is the infinite dimensional random dynamic. Why the random dynamical system? Infinite dimensional means from PD space. So a lot of concept and the theory in the dynamics like Lyapunov exponent, attractors, limit sets, etc. can be generalized to random dynamical systems or infinite random dynamical systems. Also, same. Philosophy is same. Just the different thing is the complication, the vocabulary, and some. In the case of random, there is a probability space and phase space here. In some sense, two actions. There is a driver, one direction. Because of the noisy term. A lot of real-world problem can be expressed by various type of equation, depend on environment. Because it depends on the environment. Sometimes ordinary differential equation is much better than to express the real-world problem. OD is better. From here we can get the dynamical system. This is the abstract concept. Sometimes real-world problem can be expressed as partial differentiation. That is infinite-dimensional dynamical system. Sometimes stochastic differentiation is a random dynamical system. Stochastic partial differentiation, infinite-dimensional random dynamical system. So all dynamical systems. Very nice. Many dynamics. Right. Oh, you are very clever student. Smart student. Thank you. Student, professor. Thank you. The main goal of the third dynamics, many dynamics, is to understand long-time behavior of the orbit. What is orbit? Abstract concept of solutions. Abstract concept of solutions of the equation. Orbit, what is abstract concept of solutions? Okay. From what? From topological viewpoint. That is, the subject is, we call it the topological dynamics. From a viewpoint to geometrical viewpoint, we need the geometry and bundle, and it's called the differential dynamics. And the mathematical viewpoint, we can understand the structure of the orbit. That's called the measurable dynamics. Functional analysis viewpoint, that's infinite-dimensional dynamical systems. And statistical viewpoint, random dynamics, also numerical viewpoint, numerical dynamics, etc. It's a dynamical system. Dynamical system. We want to understand the long-term behavior with this direction, with another direction, with another direction, with another direction. I think we are hungry, so I'm going to, if possible, just going to finish my lecture as soon as possible. If you do not agree, raise your hand. Thank you, everybody wants, so I'm going to. Consider, give you a simple example. You know the differential equation on the graduate courses. Left side is a vector field notation, vector notation. Right side is color notation. In the x1 direction, there is the all constant x2 direction is alpha. Alpha is constant. Color notation. Then this is a vector field. Vector field. Alpha depends on alpha is slope. Slope. Right? Then what is that? And define a map from R2 to torus, not a subset of R3. As the first component, second component, third component. Oh, not easy, maybe it's a calculus. Define such a way. Then H is a map from here to here. P with the flow torus by vector field. Vector field, so you can do this and forget it. This is not important. So, if alpha is rational, then orbit. What is orbit? Solution. What is orbit? Solution. You know, in celestial dynamics in the universe, there is orbit. planet moving. We have the orbit. So if you P is rational, then orbit is periodic, sometimes touch again. For example, if alpha is irrational, then there is no period, not period, but it is dance every point, closer that dance, depending on alpha. This is one example of the dynamical systems. Numerical solution. Professor, you are the numerical. I'm sorry, Professor, your name. So you are very familiar with the numerical method. Numerical method. What is the numerical method? Yeah, numerical method. Yeah.
Sorry, first of all, I am not a professor, so
No, you are a lecturer.
I am a lecturer.
What is different? See,
It's a bit different in opinion, so a lecturer is different from a professor.
no, I don't think so. In every world except Vietnam,
For example, professor is a level of knowledge, but a lecturer, I think, is
no, I'm to ask you to my both professors. What do you think about it? That is correct?
No, I don't think that the professor is only in high position because it depends on every person. Some students, some researchers are not even they cannot get the professor title.
Yeah, that depends on the time. In time, you will be professor. So sometimes I told you to talk, but Professor talk. Why not? No. May I ask your name? I'm sorry. Why? Thank you, Professor Pai. Yes, your concern, your research subject is numerical method. Eh? Numerical method of something. Right. Why numerical method? In literature, you can heard about the numerical something. Listen, please. To find the exact solution of the equation is very difficult, I told you. What is the numerical solution? We allow the error. Truncation error, so we allow the error. We want to find some pseudo solution, which admit the error. That is a numerical solution. Because in computer, if you draw the picture, y equal to x to the 2. In computer, if you draw the computer, y equal x to the 2, is a not exact figure. In the computer, cannot. 2 to the square root 2, square root 2, cannot. Did it? There is an error, right? So numerical method is to find the method, to find the solution, numerical solution. If we find the numerical method, one method, it is very interesting. So numerical method is we allow the error. It's a solution. It's a pseudo solution. It is very difficult to find the solution equation of the equation, and it is important numerical solution which approximate the solution. If we find the numerical solution, but it is far from the real solution, it is not much interesting. Most nearby pseudo solution, nearby numerical solution, if there is a real solution, it is interesting, more interesting. Professor, am I right? Why you told me just why? Your name? Prof. Why, am I right? I will call you. It's okay. Then Dr. Phi, if you convenient, Dr. Phi is okay. Dr. Phi, right. So I told you, abstract notion of solution is orbit, right? Abstract notion of solution is orbit. Abstract notion of numerical solution, pseudo solution is a pseudo orbit. Pseudo orbit. Easy. Same philosophy. Easy. Oh, very good, very good, very good, very good, very good, very good. Let me try the pseudo orbit. Okay, here. This is pseudo. We allow the error, uniform error. We allow the error. It's a solution. From here to here is a real solution. But jump. This is pseudo solution. Pseudo orbit. So you express mathematical value. No. Distance is less than this. Delta pseudo. I'm sorry, not it. Dr. Tao, can you read the sentence with a loud voice?
Yeah, this would be an ideal situation if we have a solution near the numerical solution we have obtained.
Very good. We obtain the numerical solution, right? By computer, usually you use the computer. Nearby is numerical solution. If there is a real solution, that is ideal, better, good. If there is no real solution, numerical solution is not efficient. The concept of representing this situation in the third dynamic is shadowing. Shadowing. So numerical analysis and dynamic are very close. Shadow means there is always exist a solution, real orbit near the pseudo orbit. Shadowing is the terminology in dynamical system. Numerical solution is the terminology in differential equation theory. We say that the dynamical system shadowing for any epsilon there is delta. Not much. A dynamic shadow means there is always the orbit. What is orbit? What is orbit? Abstract concept of what? Abstract concept of?
Solution.
Very good, very good. Abstract notion of solution is orbit. Huh? Abstract notion of solution is orbit. Okay, good. Very good. So, there is a real orbit. This is real orbit. Should orbit. Good, very good. Very good. What year? Second year, third year, first year? First year student. Undergraduate. Undergraduate or graduate? First year student. Amazing. Oh. Wow. We say that one of the rather definitely expensive. Okay, you know, it's not boring. It's not interesting. In every subject has a lot of definition. Why? Using the definition, we wanted to classify the concept. We wanted to classify the concept. We wanted to classify the concept. So every concept, every subject has a concept, right? We want to classify the concept. For example, function f from R to R is continuous. Then we can concern of the constant functions. Differential. We concern of the collection of differential functions. To understand the long time behavior of the orbit, we give the definition, shadowing and the expansive, to classify, using the concept, to classify. Definition itself is not important. This is not expensive. This is expensive. Near. Okay. In mathematics, every student will look at here. In mathematics, most important thing is a classification problem. Classification. Classify. Poincaré said what? Poincaré said what? Mathematics is the art of what? simple. Yes, Fokker said mathematics is the art of same name to different things, giving the same name to different things, right? So classify in some sense. For different things, give the same name. This is one class. This is one class. This is in some sense a classification problem. In algebra, group theory, what is most important thing is isomorphism theorem. What is the meaning of isomorphism? Isomorphism means two groups are isomorphic. Do not distinguish. Same. In set theory, two sets are equivalent. Same. What is equivalent? Equal. Two sets are equal. What is the meaning of that? The number of the set is one-to-one correspondence. In the case we do not distinguish. So we say that two sets are equal. In adjective, equivalent. Two sets are equal. What is the two groups are equal? As a set, equal. Operation preserved. So we do not listen to two groups are isomorphic, that we say identify. Say two topological spaces are homeomorphic. Say. So classification problem in mathematics is very important. When they are isomorphic, when they are homeomorphic. To understand classify the problem, algebraic topology comes out. Algebraic topology. The white shirt you. What is your name? Oh, come on. He come from the Hanoi University of Science. When I visited last year, 1 year ago, visited BSM, he was a student, he had a seminar. He is now in the third year student. When he was a second year student, he was working on the algebraic topology. I was surprised. So what do you think about algebraic topology? What is that? You learn.
Can you please rephrase the question? Sorry.
What do you think algebraic topology is? Yeah, what is the goal of the algebraic topology? Why you study algebraic topology? What is topology? What is algebraic topology? What is different between two? I'm thinking, okay, too many questions. What is topology? What is the algebraic topology? What is the difference between two things? Because he was working on algebraic topology as an undergraduate student. I was surprised. He is a Hanoi University of Science.
As far as I know, algebraic topology is the study where people use the algebraic tools to study the topology, like group theory, some sort of things.
What is the name?
My name is Dan.
Talk. Can you say a couple for us? Thank you. Yeah, algebraic topology comes up because of the classification problem. Two topological spaces are homeomorphic. We do not the same. But there is a limitation. So mathematicians are very clever. So in topological structure, give the algebraic structure. Algebraic structure in topological space. They made a group, homotopy group, homology group. Using the group, if the two spaces are homeomorphic, then fundamental groups are same, isomorphic. Not easy to classify in topological space, they are homomorphic or not. So at the beginning, they stop. Something like that. In the algebraic theory, like both of what? What is that? Okay, I'm sorry, forget it. Entropy. In algebraic theory, the same reason, entropy. When the measure space are same, equivalent. To understand, the entropy theory comes out. So what I'm talking about is classification problem is very important. In dynamical systems, same. Classification problem means when they are stable under small perturbation, If they are same. In the case of dynamical system, same means conjugate. Conjugate. Different. In the case of set theory, equivalent. In the theory of algebra, isomorphic. Two vector space isomorphic, groups isomorphic. In the case of topology, homeomorphic. In the case of dynamical system, conjugate. Not distinct, same. So when two dynamical systems conjugate, very important. Half conjugate, that is half conjugate, semi-conjugate. Half conjugate, semi-conjugate. Topological stability is semi-conjugate. Structural stability is conjugate. Then when a dynamical system is semi-conjugate, topological stable or structural stable or conjugate are very important questions. Under which is assumption they are true. Okay, for undergraduate student, in mathematics or mathematics, classification problem is very important. What is classification? We want to classify these subjects, they are equal, isomorphic, homeomorphic. Topological is better. The terminology is ugly. No more. But yeah, what's wrong? So now 40 and 45 years. Wait for a moment. Okay. Thank you. No, this is the idea. Just could say classification problem. What is orbit? Orbit is a solution. Solution. Almost. Okay. Some of this is important. I'm going to give the slowly. First, a lot of natural, real world problem can be expressed by equation. Ordinary differential, partial differentiation, Stochastic differential, partial differential, functional equation, many equations. From here, we are going to abstract. This one, abstract. After dynamical system. From OD, we got the dynamical system. From PD, we got the infinite dimensional dynamical system. From Stochastic differential equation, we got the group action dynamics is from dynamical system is what is group action dynamics? Solution is not unique. Many actions. This is one side. Sorry. Oh my God. This is from the Stochastic differential electric one is random dynamics. We can do. Of course, group action, random group action also we can have. From Stochastic differential equation, we can get the infinite dimensional random dynamical system. So this is the abstract concept. Of course, in here we have the stability problem in itself. The PD also in Stochastic differential, we can in itself using the equation we can do it. We can do it, and the abstraction we can do it. Again, the main goal of the theory of dynamical system is to understand the long-time behavior orbit from topological viewpoint, geometrical viewpoint, theoretical viewpoint, functional viewpoint, statistical viewpoint, numerical viewpoint, etc. Tomorrow I'm going to talk about fundamental theory of dynamical system and then application of dynamical. Maybe you are interested in the first lecture, application of dynamical system is related to AI related subject. So from now, why I finished earlier because to have some more question time and discussion time. We can have discussion time. Any question is okay in mathematics. If I don't know, I'm going to ask to another professor and we can discuss about any question. Ah, you are here. So Dr. Why? Yeah. Any question? Do you have any questions? Very good.
Yes, I have a question about one problem in the first lecture. I absolutely don't understand how can we use the same name for different things in mathematics. Because as I know, different things must have a different name. So I don't understand why math we can call different things in the same name. Can you give some example about different things that we can call it in the same name?
Very good question. Very question. What do you think about Dr. Tak? About her question? Can you answer instead of me?
Yes, I think it's an attractive question. From my view, perhaps we put the name for the notion is based on the logic and intuition, based on the structure, what we feel about the notion, and we put the name to give us the feeling, the intuition of the concept. So exactly, her question is very interesting. Perhaps it's not exactly same thing. Yeah, they are different things, but they have some common structure. That's why we put the name.
Are you satisfied? No.
Okay.
Excuse me? Yeah, you answer. She's going to answer. Very good. Thank you.
I would give one example for different things with one name. For example, we have length in one-dimensional, we have area in two-dimensional space, and we have volume in three-dimensional space, and we have just one name, measure. So when we talk about measure theory, it means that we have about the theory of length in one-dimensional space, and the area theory in two-dimensional space, and volume of object in three-dimensional space. This is one example. Thank you.
He's going to go ahead, please.
No, I'm finished.
He's going to take a photo.
Oh, okay.
So please, Professor Wayne. I'm sorry. What about your opinion?
Yeah. Different opinion we can do. Very good. Then this is the art. This is the art.
Yeah, it is two sides of an art. I mean that for mathematics, as Bangori said, mathematics is an artifact with the same name for different things. Conversely, if you are poetry, then you can find different name for the same thing. I think it's two sides of the same thing. Whether you are an artist, a mathematics artist, or you are another artist coming from poetry, for example, then you always try to find different name for the same thing. But mathematics is do something conversely. You know? So we want to. This is the advantage of abstracting. I mean that you say very exactly that mathematics is containing abstraction, right? Abstraction means that we want to generalize to find abstract structures, and that you can use that structure to apply to many other things. Like you can use the same, you can use the old experience with the real number to work with topology in the same way. This is advantage of abstraction. You can use the old experience, the old computation, and the old calculation in the new object. Actually, provided that it has the same structure. And as I said at the beginning, the important thing is we have to find exactly the structure that the object has, so that you can apply the old experience for the new thing. Thank you.
Thank you very much. Okay, wait a minute. I want to ask the Professor Venice to listen his opinion.
There are many ways to put same name for the other object. It depends on what are you interested in it. For example, young boy and the older person, we can put in the man because we consider only the guy who is the person, the sex of this person. Yeah. Okay. And when you have so many internet operators, you want to characterize them, and if you are interested in his character, you can put the same name for this object. For example, give an example. The length, the error, the volume, the character is the matter. So the matter we keep that.
Thank you very much. Thank you very much. Thank you very much. May I ask to Professor Song?
Yeah, please answer.
An example you mean?
Yeah, she asked some example.
Oh, so yeah, this is. I think that.
Not only example, any comment? Any?
Can I comment on her?
Oh yes, yeah. You first. Okay, good. Yeah, you also algebra pro. We met in the classroom, right?
Yeah.
1 year ago in Biazum.
We met sometime.
Right, good. What is your name?
Chị Đăng Dương.
Ching Tang Zhe. Okay, go ahead.
Can I speak in Vietnamese because I think
Yes,
my
go ahead.
English is
Yes,
not good
okay.
enough
Then
to
I'm going to translate.
express
Don't worry, go ahead.
Yeah. Ý là câu hỏi của chị là tại sao ông Bonke lại có thể nói là toán học là một nghệ thuật đặt cùng một tên cho các sự vật khác nhau, thì em nghĩ là tất cả các thầy ở đây đã nói được kiểu toàn bộ cái ý của nó rồi. Ý là như này, em đã nhận ra một điều là từ ví dụ của thầy ngồi dưới kia là thầy lấy độ dài, diện tích và tích để nói về một cái gọi là độ đo ấy, thì thực ra như này, khi mà có nghĩa là toán học là chúng ta sẽ thường trừu tượng hóa và gọi là khái quát hóa lên ấy, để cho nó dễ hiểu hơn ấy. Thì ví dụ như là trong trường hợp một chiều chúng ta sẽ kiểu hiểu nó theo kiểu là ok, độ dài, nếu mà hai chiều thì là diện tích. Nhưng ví dụ như là mình khái quát hóa nó lên thì mình dùng cùng một cái là độ đo. Em bắt đầu không biết phải nói như nào, nhưng mà nó rất là hay, cảm giác nó rất là hay. Nghĩa là khi mình đặt cùng một tên là bởi vì mình khái quát nó lên, chỉ vì đơn giản đấy thôi, chỉ vì mình muốn khái quát nó lên để nghiên cứu nó dễ hơn. Có nghĩa là ví dụ như là khi mà chị nghiên cứu về độ dài, diện tích hay là thể tích, nó đều có chung một tính chất gì đấy liên quan độ đo, thì khi mình khái quát nó lên thì mình cần một cái tên để đặt cho nó cho dễ hiểu, để cho nó dễ nghiên cứu, và mình cho mình thêm một cái góc nhìn mới. Thế nên là mình đặt ra một cái tên để dùng tất cả mọi cái thứ đấy, mặc dù nó trông có vẻ khác nhau nhưng thực ra nó lại là giống nhau. Thì khi mình khái quát nó lên thì mình cần một cái tên, và cái tên đấy thì nó dùng thì em cảm thấy khá là hay. Phải nhờ đến ví dụ của thầy ở ngồi dưới kia em mới có thể hiểu được toàn bộ đúng chính xác cái câu nói đấy của con kè.
Thank you. Got it?
Yes.
Okay, thank you.
Very interesting answers.
Thank you very much for all the answers because they are both very interesting, and maybe they give me some so thank you very much for the answers. It helped me so much.
Thank you very much. Any other question or comment? Doesn't matter. Okay, very good. May I ask your name?
Hello, Professor Lee. My name is Vũ. I'm from the University of Danang.
Oh.
Okay. So I'm a major in business administration, but I'm favor in mathematics. So I'm come here. I bring my question. I have a concern and I'm confused about the dynamic system and system dynamic. Can you explain it? Because in the business, the system dynamic is very popular and applicable in the real situation.
Okay, got it. Frankly speaking, I don't know exactly, but Tom, can you help me?
In fact, I also don't know the system dynamic.
Okay, dynamical system, so depend on the situation. As far as I know, they use the terminology of dynamics very well. So, dynamical system in the Oxford Math Institute, I already give you the definition. They define Oxford Math Institute. If you visit the website, dynamical system is a common sense definition of dynamical system. Common sense definition of dynamical system. So, conclusion is this one. The notion of dynamical system is not unique. Depends on the case. In physics, in chemistry, in engineering, various concepts of dynamical system. So that's why they define such a way. Common sense definition of dynamical system is natural phenomena evolving in time. If a system or the natural phenomena contains in time inside, that is dynamical system, dynamics. So my city, I live in desert. The place is dynamic desert. Dynamic Danang, for example. So meaning of dynamic is active in some sense. Dynamical system is different. In some sense, Y system, differential equation, not only one. In the vector field phenomena, is a system. You saw the system. Vector field is expressed by the scalar function 1, 2, 3, 4. That is a system. What is the English system of differentiation? System of differentiation. I wrote. Where is the pointer? I'm sorry. Oh, good question. Very good. Let's go back. What is the example? Equation. Example of this one. Okay. This one is a system of differential equation. Not only differential equation. System. Right? In what's the Vietnam language system? System of differential equation. Not only one equation, two equations, three equations. That is system. System of differential equation.
Yes, the system of differential equation in Vietnamese là hệ phương trình vi phân. Hệ phương trình vi phân.
What?
Yes, sorry, I speak maybe too small. System of differential equation in Vietnamese is hệ phương trình vi phân.
Hệ phương trình vi phân. So it's a system, dynamic system. Not only one equation. So we put the name is dynamic. I didn't ask to Ponkare. I did not meet the Ponkare. He passed away, so I don't know. He put the name. But I think this is motivated from the system. System. Right? System of differentiation. My answer is very. Are you satisfied? Are you okay?
Yes, yeah.
Thank you very much. It's a good question. Any question? Maybe you have some question. A lot of questions. Any question? Do you have any questions or comment? Do you have any question?
before I don't understand clearly for follow. So now I understand more than. So I ask some questions. You can make make so clearly to grow in natural nature. Yeah.
I don't understand the talk. Can you help me? What? What is the question? Flow. Why you put the name flow? I see. A good question. Okay. What is orbit? Orbit is a solution. Solution is smooth. Solution is orbit. Orbit is solution. Solution is a function. N-dimensional space on the plate, for example, solution curve. So because of the continuous dependence, like water flow, on the river, water flowing, that is dynamics. That is dynamical system. We can express the situation by dynamical system. In PD, that kind of phenomena can be expressed by Navier-Stokes equation or something, right? But then we can express that by dynamical system. That is dynamic. So if you, on the river, if we put some small boat, then go like a flow. That's why we call the name flow. Dynamical system is flow. Good. Very good. More intuitive. Flow is more intuitive. 5 minutes more. So I have to lecture until 12 o'clock. Otherwise, Professor how angry at me. Yeah, please.
In the definition of topological stable, you say if B and C to dynamical system on A, then you say B is close to C, and I don't get what do you mean exactly by close to?
Very good mathematical question. Here, look at here. You're from also Harvard University Science. Oh, very good question. Okay, in dynamical system, we have two types of stability. First one is phase space is fixed, and the dynamical system fixed. Then dynamical system one differentiation fixed. Then if you take a point and the nearby point go together or not, that is stable. If go together nearby base point, that is stable, local stable. Second, phase space here, differential equation here, and the two system. Ordinary two system, one OD, another OD. We can give the matrix between two OD. If the OD are close, then their solution, how much different? If the two differential equations are close, then the solutions, how much different? If the solutions are same, conjugate, we say that structure is stable. And if the solutions are semi-conjugate, then we say that topologically stable. So we two types stability. First one is perturb the point. Equation is one. Perturb the point. Lyapunov stable, exponentially stable, something like that. Second one is perturb the equation, perturb the system, perturb the dynamical system. And how much different the orbital structure. That is another type of, we call that is a global stability. Perturb the system. Without perturb the system, the equation, only the system, one system. We can think about the stability problem. You understand? You understand? You understand my point?
I want to comment on this.
Okay, in Vietnam language is better. Good. You are my teaching assistant. Very good. Very good.
Do you mean close here when you define the topological stable is close mean nearby or
Nearby.
nearby, not like close in topology, right?
Yeah, but of course we have many type of closeness.
So how close it is? Like
Yeah, using just the matrix, you give the topological viewpoint or differential viewpoint. Differential viewpoint. For example, F is from R to R, G is from R to R.
yeah.
But between F and G, we can give the distance.
Yes.
Right?
So how close is the distance? Like
Right.
how small is it?
Yeah, there are many different type of distance.
Yeah.
Under the distance, how much is same, how much is similar?
Is there any like epsilon that if the distance is more than that epsilon, then there's no continuous mark between
Right,
those
something
two?
like that. Definition is we can define. We can define many ways. But one of them is that one.
Okay. So is that epsilon is depend on the regularity of the orbit or anything?
Yeah, complete the detailed definitions. I need a blackboard.
Yeah.
Oh, here's a blackboard.
Okay.
Okay, good. I am to comment. That is just 2 minutes or 3 minutes. Part or one minute. Nice. So one comment here. Okay. This is the collection of all solutions of ordinary differential, partial differential, stochastic, doesn't matter. It can collection of all solutions. Can be topological space sometimes, superlative space doesn't matter, sometimes manifold measure space doesn't matter. But here we have one system. This is, you can think, this is the abstract notion of differential equation. One ODE, one PD, doesn't matter. Phase space, we can think about the very close, another ODE, another PD, another dynamical system. If they are close, this is important. How much closeness? There are different type of closeness, many concepts of closeness. If they close, under this one, there is a dynamical system, orbital structure. Under this one, there is a dynamical orbital structure. How much same? Solutions, how much same? That is the global stability. Another thing. Local stability is space here. This is fixed. Do not change this one. If you take a point, there is a orbit. If nearby, x and y nearby, how much close and how much is similar? That is the stability also. This is a global stability, topological stability, structural stability, many stability here. This is the Lyapunov stability here. It's okay for you?
What I mean is how do you express the term close by
Loud voice, cannot hear.
I mean how can you express the term close? I mean how you express the term close by symbol. equal.
More the exact definition of closeness. Oh my God. Oh, by formula. Wow. Okay. Can you explain? Is that me? No? Okay. For example, this one. This one. For example, X is topological space. You are already know the topological space. So D C0 P psi. What is P? P was the function from X product R to X. Right? This one is a dynamical system. Huh? So if X is compact, we can do this is we can do this one X in X, and the time belong to 0 to 1. So distance of B T of X psi T of Y T of X such a way. So ugly definition. But we can give the C1 this distance between P and Z psi. We can define many concepts here. So this is it means it's a definition of this one. Okay, this is difficult. Then the F and the Z are, for example, simple example, R to R. We can define B, C, 0, F, G. This is a distance, not what? We can define such a way. Supremum of X in 0, 1. We can do this one. The distance between Fx and Gx. And DC1, Fg, something like that. But here, DC0, Fg, and plus what? Supremum X in 0, 1, and this F prime X minus G prime X. This is C1 distance, C2 distance. We can do this one. So, in the sense, we can give the distance between two dynamical systems. If they are close, then the orbital structure close or not, dynamics are close or not. Sorry, it's time to finish. We are hungry, so we are going to have lunch. During the lunch time, you can, if you have any question, please. Okay, this is the end of my second lecture. Thank you very much for your joining. Let's enjoy the lunch. Let's enjoy the lunch. Maybe Biasmo are going to support our lunch. Right? Am I right? Very good. Announce.